So now that we have the approximate sampling distribution for this estimator p hat, it's up here in the box, we are going to use that to develop our confidence tools, our inference tools here. So it's the same set of tools, a confidence interval and a hypothesis test. With a hypothesis test, what we are doing is hypothesizing or claiming a value for the population proportion. And this is the claim that we are going to try to find evidence against. So just like before, we are aiming to partition all of the values for P and split them up into two parts and gather evidence to try to show you that the portion in the null should be rejected and leave you with the alternative, which is one of either the two-sided or a one-sided alternative. Now, the idea here is that we know the sampling distribution. So we'll take a sample, we will get a size, we'll get a number of successes, and then we'll get something called little p hat. And this is the observed sample proportion. Now remember, uppercase letters typically refer to the function or the random variable, the estimator, and lowercase letters refer to the observed value or the actual numerical estimate. So this right here would be our point estimate based on the sample. So at this point estimate has to follow the sampling curve that we know. It has to follow this curve for the p hat values. So essentially what happens is now the null hypothesis sets the center of the sampling distribution for p hat. So over here we've got a capital P hat axis, and we've observed this sample value, little p hat. And so what we are interested in is the area in this tail. Now, as always, we are going to standardize this to be able to perform this calculation. So when we standardize it, we'll get our standardized variable. We will take the observed value p, subtract from it p naught, and divide by the sample standard error. So the sample standard error is essentially the standard deviation of our sampling distribution. So it would be p naught 1 minus p naught all over n. The reason we are using p naught is because of the null hypothesis. We are assuming that this is the value that our distribution is centered on. So we go ahead and we compute from there. Once we standardize this, this turns into a standard normal distribution. So this is a z value. We will end up with some score here, and then the p value will be the tail area. Now, if it's a two-sided test, we will use a doubling of the tail area, or if it's a one-sided test, we will use the appropriate direction. Now, some of you might be picking up on one idea here, and you say, well, hold on. Remember that in Chapter 3, we used a continuity correction when we replaced the binomial discrete distribution, or any discrete distribution, with a normal distribution, or this particular continuous distribution. And so the continuity correction basically entailed adding or subtracting a 0.5 from the number of successes to adjust for a bar width. Now, in this context, we don't have the actual number of successes. So in our Z statistic, we've got p hat minus p naught all over the square root of this value here. In order to be able to see how you could implement the continuity correction, you would have to essentially turn both of these things into counts or numbers of successes. So if we were to pull in the 1 over n factor into the root, we would get this, and now we would have to add in this 0.5. So here we would have our plus or minus 0.5. which means that if we wanted to go back, this would also be equivalent to the following. We'd have our z, and if we now factored out an n from everything, we would have p hat minus the hypothesized p naught plus or minus 0.5 over n divided by the original thing that we had before. Now, this continuity correction is essentially a term that goes like 1 over n. The bigger n is, the less you will notice. This continuity correction technically will improve your answers, but as we're going to find out in a few minutes when we talk about confidence intervals and in the next section, it's kind of fraught with a bit of headache. The continuity correction is less important for large n. Very annoyingly, it's inconsistently applied in the textbook homework questions, which is really annoying. And it's ignored in confidence intervals and in the two sample methods. So all of this is to say, we are going to ignore it. So that's what we are going to take. We are going to ignore the continuity correction for these inference methods. There is a difference, and yes, it will improve your results as compared to the exact, but for the purposes of this section, it will suffice if we ignore it. There is a huge background literature on how you can best approximate situations like this. It's a rabbit hole that we're not going to go down right now. We are just going to ignore it. So when you perform your hypothesis test, feel free to ignore the continuity correction. There is only one question in the textbook that uses it, and every other hypothesis test question does not. So it's really a bit of a head scratcher there. So a confidence interval works very similarly. We are going to have our point estimate, and what we're trying to do is give a margin of error. The margin of error has to incorporate the confidence level plus the standard error. So there's going to be a critical Z star that corresponds to the confidence level multiplied by the standard error, or the square root of the sampling distribution standard or variance. So the standard deviation of the sampling distribution. The confidence interval works the same way. What it does is it sets bounds on where we think the true population proportion lies. There's a bit of a headache using it. The result is in terms of p. But how am I supposed to estimate p when I don't know what p is? So if I need p to estimate what p is, that's kind of circular. So what we're going to do is simply replace it with p hat. It's our next best guess. So the idea is that when we go ahead and form a confidence interval, we are going to have p, the thing we are trying to estimate, as being trapped between the point estimate and the appropriate margins of error. So we'll have a p hat, z star coming from the normal distribution, p hat 1 minus p hat over n, p hat minus z star square root p hat 1 minus p hat all over n. So these things just take time to develop, but once you have them, using them feels the same way as it did in our previous work. So for example, on the PDF sheet that I've attached here, I've got a question regarding seat belts. And so this is a proportion question, and we've been given some sample data. Now, we've been told that the sample size is 117 and the number of successes is 68. So you could easily estimate your sample proportion as 68 by 117. Now in part A, what we want is a 95% confidence interval. And to do that, we need to determine Z star. This is a two-sided interval, so that means the appropriate Z star takes the standard normal distribution and says, where should I stand so that the central area is 0.95? Now, in R, you could calculate this using the Q norm result. So in R, Z star is going to be Q norm. We want to turn this into a left area problem. So not only do we have 0.95 in the central bump, we also have the remainder of this tail area, 0.025. So this would be 0.97501 for the standard normal, and this is about 1.96. So in order for you to calculate this, unfortunately, R does not have a built-in routine. So that means you have to calculate this manually using R. Now I've posted a little sample code in this file as well that gives you the basics of constructing this. You're essentially just typing in all of these formulas into R and having it calculate. I would recommend you type the parameters in first, the sample statistics, and then just leave everything generic in general after that. So in R, you would calculate this manually. And when you do that, you should find that your confidence interval will end up giving you 0.4918 up to 4 decimal places and 0.6706 up to 4 decimal places. Again, the code for R is listed there. It's nothing more than simply using the formula that we developed up here. Sorry about this. Just using this formula and manually constructing each of these elements and putting them in. A hypothesis test works similarly. So in the second part, we are asked something about a hypothesis test. And the null hypothesis is a statement about no change. So here we are interested in, is there evidence to suggest that more than half wear seatbelts? So the no change statement would be this, 0.5, whereas the alternative is what we think is true. And we think that more than half wear seatbelts. So the reality is that the null hypothesis is really a less than or equal to. So here's our 0.5. Remember that all the values of P can ever go from 0 to 1. So the null hypothesis would be here, whereas the alternative hypothesis would be there. We are going to try to find sample evidence to show that we should not believe the null. So the sample evidence we have is, as before, we are given these the statistics from the sample. We can calculate the p hat very easily. And we are going to build our problem. And so all p hat values follow this theoretical sampling distribution. The center of the distribution is set by the null hypothesis. Our sampling result is about 0.581. So it's somewhere around there. This is our observed p hat. Now we are performing a right-tailed test. We are going to standardize this and and turn it into a standard normal problem. The standard normal problem is centered there at 0. And so when we go ahead and we calculate this as a standard normal problem, what we have to do is compute the z as we normally would. So we would have z is p hat minus the 0.5 that's been hypothesized, 0.5, 1 minus 0.5 over 117 for n. You do all the calculations, you'll find that you get a z value of about 1.752. And so we could already get a sense of what this tail area is going to be. The p-value is simply the probability that z would be greater than or equal to 1.752. In R, this would be a right-tailed problem, so you'd have to go 1 minus p norm 1.75201, and you're going to end up getting about 0.0 0.039 and some change. 0.0395. And what this does is we can now use this as evidence to make a suggestion. Since our p-value is greater than the alpha, the 2% significance level, we cannot reject the null hypothesis. The evidence we have is not strong enough to say there is an increase. If our significance level was different, if it was higher, we might be able to make that argument. Now note, there is a command in R to calculate the exact confidence intervals and hypothesis tests using the binomial distribution. And you could use, in R, you could use a test called binom.test. And it will perform sampling, or it will perform inference procedures. We are not going to use this in our course, but it exists. And it's a nice comparison to try to show you that the continuity correction helps and the values we get are close. Now remember here, we are not using the continuity correction. So just be aware. Yes, you could, and if you did, you would get a slightly higher p-value in this particular problem, but the result would still end up being the same. You could not reject the null